So far, we've looked at graphs that can be written in the form of y equals a over x minus b plus c. So we've analyzed those types of rational functions, and they are called rational functions because they do have a fractional value, but there's really more to being a rational function than just having a fraction in this position. So we're going to define that more clearly today. We have a rational function in the form of f of x can be written such that we have a polynomial in the numerator and a polynomial in the denominator, where the polynomial in the denominator cannot equal 0. So a rational function, rational numbers are numbers that can be written as an integer over an integer. Rational functions, on the other hand, are functions that can be written as a polynomial over a polynomial. And that polynomial in the denominator, again, cannot equal 0. And here's one example. You can see I have a form of a polynomial, first-degree polynomial of 4x in the numerator, and another first-degree polynomial in the denominator of x plus 2. And so we know the top graph is a line and the bottom graph is a line. However, the quotient of the two graphs is something very different, and it is called a rational function. Here's another example of a rational function, g of x. I have a degree 2 polynomial in the numerator as well as a degree 2 polynomial in the denominator. And naturally, having these squares is going to cause the graph of this function to look differently than this function. So let's continue on. Now, we noticed in our graphs in the last section that we did have a vertical asymptote. And we have vertical asymptotes quite often in rational functions here as well. And we have the concept, if we look at the denominator of our rational function, whatever causes our denominator to be 0 is going to be a point of discontinuity. For instance, in this function f of x, I can see that an x value of negative 2 will cause me to have a 0 in the denominator. So an x value of negative 2 is a point I can't substitute in. Therefore, we call it a point of discontinuity. And a discontinuity is going to be, if you think about it, when you graph a graph, if you ever have to lift your pencil, you have something called a point of discontinuity. And we have some different ways that discontinuities can take place. They can take place as vertical asymptotes. They can take place as holes. So I'm going to actually go up to this example up here, and then we'll clarify it more later with some other examples. And we're going to look at these two to show that we have kind of some differences in how we determine whether we have a, quote, hole in the graph or we have a vertical asymptote. So if I go back up to this f of x graph, this f of x graph, as I said, I can't plug negative 2 into the denominator. Now, negative 2 inputted here is definitely causing this denominator to turn to 0, but it doesn't cause the numerator to turn to 0. If that type of phenomenon takes place, if both the numerator and denominator are 0 by an input, that's going to cause us to have something called a hole. So in this case, in this graph, my x equals negative 2 will actually be the equation of a vertical asymptote. Now, we go over to g of x. G of x, I need to factor that. And that denominator is good old difference of squares. Numerator, on the other hand, I can see x times x is going to give me the x squared. And I know the product of the last two numbers has to be 2, so a 2 and a 1. And if I do a plus and a plus, the 2x and the 1x add to the 3x. So now I have the factoring. Now, I have points of discontinuity. I can see I have an issue if I plug in an x value of negative 2. I also have an issue if I plug in an x value of 2. Both those are places that we call points of discontinuity because they cause me to make my denominator undefined. I can't have division by 0. If I plug negative 2 in here and here, I get this factor to be 0, and this factor becomes negative 4, but the product will be 0. I'll have division by 0, and that we know in the real number system we can't have that. Likewise, again, 2 plugged in here causes me to have a 0 in this factor. Not in this one. This one would be 4, but 4 times 0 would cause me to have a 0 in the denominator. Now, those are points of discontinuity. But notice that if I plugged negative 2 into this factor, this factor, this factor, this factor, that it causes my numerator, an input of negative 2 would cause my numerator to also turn to 0. And if both the numerator and denominator turn to 0 with an input, that is a point of discontinuity, but it actually graphs as a whole. We have a whole at x equals 2. I'm sorry, x equals negative 2. Negative 2 is the number that makes this turn to 0. We will have a vertical asymptote, however, at an x value of 2. There will be a vertical asymptote at x equals 2 because if I plug 2 into this function, plug it here, 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 it only makes my denominator turn to 0. 0 times the 4 would make this turn to 0, but inputting 2 up here does not cause the numerator to be 0. So discontinuities in a graph, points of discontinuity are going to be any place where our input causes our denominator to be 0. Now, if our numerator and denominator do not have a common factor, as is the case here, then the 0 for this denominator will cause me to have a vertical asymptote, as I said. So there is no common factor here. Therefore, the 1, 0 only to the denominator ends up being a vertical asymptote. However, when our p of x, or our numerator and denominator, have a common 0, which is the case with our g of x function up here, we had negative 2 caused both the numerator and denominator to turn to 0, then those values are going to be the location of where we have a whole. And we'll get more into, again, that information as we look at a few further examples. Now, next topic is to look at what is a horizontal asymptote. And we had a horizontal asymptote in our graph that we looked at in the last section. When we looked at this type of a graph, we said this graph had a vertical asymptote at x equals b, because that's what caused the denominator to turn to 0. And so we'd go to our graph, say this is an x value of b right here, and we would sketch in that vertical asymptote. Now, this graph also had a horizontal asymptote. It's relatively easy to see. This fraction can never be 0. We can put in different numbers for x, and this fraction, the numerator will stay the same number because it's a constant, some number, and the denominator can get really, really big, but that fraction can never be 0. It can get tiny, but it can never turn to 0. Therefore, remember, we have a horizontal asymptote at y equals c. That was in last section, so it was really easy to see what makes the denominator 0. Boom, there's going to be my vertical asymptote, x equals that value, and that fraction can never equal 0, so boom, y equals c is going to be my horizontal asymptote. We have a little bit more work to do when we have rational functions that are written in other forms. And so here are some generalizations, but we're going to look at examples, and that will make it a little more clear. So if I have some type of a rational function, and it's a polynomial, and I have some leading coefficient of ax to the n, and remember this n has to be some whole number. It can't be a fraction to be a polynomial. And we have, again, a polynomial in the denominator. This a and this b could actually be the same number, and these n and the m could be the same power, or these are going to be our degree of our polynomial. So we have some polynomial on the top, some polynomial on the bottom. It's a rational function. If the exponent in the denominator is larger than the exponent in the numerator, then the denominator is going to get bigger faster than the top, and when x gets very large, our graph of f of x is going to get closer and closer to a y value of 0. For instance, here's one example. I have a x squared plus 2x plus 1 in my denominator, and I have an x cubed plus 4, in my numerator, and an x cubed plus 4 in my denominator. When we think about horizontal asymptotes, think about what happens when x gets very, very big. And when x gets very big, these numbers, these three values, are not going to do that much to affect the value of the top and the bottom. For instance, if I plug in a million, I square a million. That makes it huge. It becomes 10 to the 12th power. I plus add on twice a million plus 1. Definitely the 1 doesn't do a lot, but squaring the million does so much more than adding on twice that large value. In the denominator, taking that million and cubing it, that does way more than adding on 4. So in essence, this fraction is close to the input squared over the input cubed when x gets very, very big. Now, the denominator is going to get way bigger than the numerator. Therefore, since the denominator gets way bigger than the numerator, my terms are going to keep getting tinier, and therefore I have an asymptote at y equals 0. Now, on the other hand, if the numerator's exponent, so this exponent is larger than the denominator, as is the case of this polynomial function or this rational function, here I have my exponent in my numerator being larger than the exponent in the denominator. That's only an exponent of 1. When I put in very, very large values, the top is going to get so much bigger than the denominator. Therefore, I actually won't have a horizontal asymptote. The graph is just going to keep getting bigger and bigger and bigger. As x gets larger and larger, y will get larger and larger. Now, what happens if m and n, or these two exponents, are the same? Kind of like the case where I had right here. So if your exponents are the same, or the degree of the numerator and denominator is the same, and here's another example. I have a square as the degree of both the numerator and denominator for my rational function. It ends up that these two coefficients as a fraction are what my y-coordinate is going to get closer to. And we could do is a table of values and put this into our grapher and let x get very, very big. And we find that the y-coordinate of the quotient of these two will get very, very close to 2/3. Never get there, but it will get very close to. So we say it's y equals 2/3 is really, or excuse me, a over b is the limit, or y equals 2/3 in this specific example would be what the horizontal asymptote would be. So in here, as x gets very, very big, these two terms are most of the value for the y value will come from these two terms. And notice that the x squares would cancel, and you'd be left with 2/3. So once again, to reiterate, if your denominator has the larger power, then as x gets very big, you're going to have a horizontal asymptote at y equals 0. If your numerator has the higher exponent in your rational function, then the numerator is going to get way bigger than the denominator. Therefore, you won't have a horizontal asymptote. And if the two exponents are equal, then you're going to have a horizontal asymptote, and it's going to be at the line y equals whatever the coefficient is here as a fraction, a over b. Now, on the bottom of this page, let's finish up here, and we have to find where we have points of discontinuity. And then we'll actually identify what type of discontinuity we have. So I have y equals, and notice this does look different from what we had in our last section. I have 3 over, and now I have a quadratic down in the denominator. So it is a rational function because it has a polynomial of degree 0 in the top and a polynomial of degree 2 in the bottom. Now, to find points of discontinuity, you're going to want to factor that denominator. That's why we emphasize factoring a little in the last few days. So I factored that polynomial in the denominator, and I can see I can't plug in -3 and I can't plug in 4. Now, notice that -3 and 4 do not cause my denominator to turn to 0. Therefore, the x equals -3 will actually be the location of a vertical asymptote, as will x equals 4. It's going to be kind of an unusual graph. It's going to look something like this, where it's going to have a vertical asymptote at x equals -3, one at x equals 4. And then let's go back to the idea we just did. Notice we could actually find what the horizontal asymptote is, or if there is one. The degree of the top is only 0. The degree of the bottom is 2. Anytime we have our denominator have a degree larger than our numerator, we're going to have a horizontal asymptote at y equals 0. So this would actually have a horizontal asymptote at y equals 0. Now, in order to find out how that's going to graph, we basically would have to plot quite a few points. Okay, and we'll get to that a little bit later in this video. Here's my next one. Now, I know in order to find location of points of discontinuity, I need to find where the denominator is equal to 0. Now, notice something. I could go through the algebra of solving this, but it's impossible for 3x squared plus 4 to equal 0, because if I solved that equation, I would have to have 3x squared is equal to negative 4, and I'll stop right there. It's impossible to take 3 times the square of a number and get something negative. So this will not have any points of discontinuity. In other words, there will be no holes, there will be no vertical asymptotes in this graph. Now, let's look at it a second and see if there's going to be a horizontal asymptote. I see again that the denominator exponent is larger than the numerator. So the degree of the denominator is larger than the numerator. So we actually would have a horizontal asymptote at y equals 0. And then to graph this, we would basically have to plot a lot of points. But we don't have any points of discontinuity. There are no vertical asymptotes or holes. So let's turn. Now we're going to graph a few things, as I said earlier. So we have a couple functions here. Let's look at this first one. Well, I'll get it on the screen. There we go. And I already factored it for us. And notice if I plug negative 1 in place of x, I have my denominator turn to 0. And if I plug in negative 5 in place of x, I have my denominator turn to 0. Those are points of discontinuity. Now, they are specifically going to be vertical asymptotes, and I kind of wrote over that. So I have a vertical asymptote at x equals negative 1 and at x equals negative 5. Right, because they don't make negative 1 and negative 5 do not make the numerator turn to 0 as well. So we're going to have vertical asymptotes. So I went through and I dotted in my x equals negative 5 and dotted in my x equals negative 1. Oops, right here. Now I also could see that the degree of the numerator was 1 and the degree of the denominator was 2. And since the power of the numerator is smaller than the power of the denominator, we were going to have a horizontal asymptote at y equals 0. Now, in order to get the rest of the graph, I plotted a whole bunch of points. I plugged in negative 7 in place of x. I plugged in negative 6 in place of x. And then I found that if I plugged in values that were in between negative 6 and negative 5, that those values were going to get very small in the negative direction. And I basically had a branch that was here. Likewise, I plugged in negative 4, negative 3, negative 2, got these points. And it ends up, this graph has kind of a U-type shaped in between these two vertical asymptotes. And then once again, I plugged in some points on the other side of negative 1. So plugged in 0 and 1 and could plug in 2 and so on. So these rational functions can have really, really odd-looking graphs. Now, next one. Again, already in factored form. Notice that the denominator turns to 0 when I input negative 3, but it also makes the numerator turn to 0 when I plug in negative 3. So I have a discontinuity at x equals negative 3, but it's not a vertical asymptote. It's called a hole. I will have a hole at x equals negative 3, and we'll actually find the coordinate of that hole in a second. Now, algebraically, we know we can reduce these two factors of x plus 3 down, since we have it in factored form. And then this graph looks like it's going to graph the line y equals x. Now, this function and this function are not exactly the same because I know I can't plug negative 3 into this denominator. So this graph and this graph look the same with the exception of this graph actually will not allow me to have negative 3 input. So I graphed the line y equals x. And now I have to identify by plugging negative 3. I can plug it right in there and find out that there's a hole right there at the point negative 3, negative 3. The hole takes place at an x value of negative 3. This is the actual coordinate of the hole. Now on part C, we get something very similar happening. I'll cover up the picture here a second. I take my degree 2 in the top and my degree 1 in the bottom. And I actually know, if I think about the horizontal asymptote, that since the degree of the top is bigger than the bottom, that I won't have a horizontal asymptote. There won't be one, because the numerator is going to get larger than the denominator, and that means as x gets very, very big, that my graph is going to shoot up to positive infinity. Now, to see the discontinuity, I can definitely tell from the original that -1 causes my denominator to turn to 0. But in order to find out whether I have a vertical or horizontal asymptote, I need to factor that numerator, good old difference of squares. Now, notice if I plug -1 in here and I plug -1 in here, I cause both the numerator and denominator to turn to 0. Therefore, that is not a vertical asymptote at x equals -1. I will have a hole there. Now, how do I figure out what the coordinate is? Do the simplifying. So cross out these and reduce those down. And this reduces down to x minus 1. Now, if I take -1 and plug it in here, I get -2. I know I have a hole at the point -1, plug -1 again in there, -2. Now, how do I graph this function? I need to graph its reduced version, the y equals x minus 1, which is going to be a line. But then at the location of -1, -2, I have to put a hole, or it's called a removable discontinuity. So I graphed the line. Y-intercept was -1, slope was 1, graphed my line. But then I had to go back and remove that discontinuity. The graph of good old y equals x minus 1 is the whole line. But the graph of x squared minus 1 over x plus 1 is the line missing the hole. Now, the last part, we're just going to do a couple more examples, look at a couple more examples of finding the horizontal asymptotes. Okay, and so when I look at this graph, I can see that if I take 2x plus 1 equals 0 and solve, I get x equals -1/2. Now, that can either be a hole or it can be a vertical asymptote. If I plug -1/2 into the numerator, I don't get 0. Therefore, I will have a vertical asymptote at x equals -1/2. Now, I look at the numerator and denominator, and I see that I have a degree 1, degree 1. They have the same degree, which means this fraction, -4/2, which I can reduce to -2, is the equation of the horizontal asymptote. So I would know right now that my graph has here's the x-axis, the y-axis. I know I have a vertical asymptote at x equals -1/2, and I know I have a y-asymptote, or a horizontal asymptote at y equals -2. And then I'd have to plot some points. Now, I want to show you, we don't have any holes, but if we take this graph actually and rewrite it in a different form, we could actually figure out that this equation that I wrote here is actually equivalent to this equation. If we did 2x plus 1 and divide it into -4x plus 3, we can see that if I put a -2 here, and -2 times this would give me -4x, and -2 times this would give me -2. And if I go through and subtract, that minus that drops out, and 3 minus -2 gives me 5. And so I could write it as -2 plus I have a remainder of 5, and then I write that over the divisor. Now this actually looks a little more like the form that we had last week, because we can see that if you put -1/2 into this denominator, that causes me to get the vertical asymptote. And we can see that that fraction will never be 0. Therefore, y equals -2 will be our horizontal asymptote. So this equation actually is very similar, although it's kind of in a hidden form, to what we had done before. Okay, finishing up, just finding the asymptotes. First of all, Degrees are the same. Therefore, if there's a little 1 coefficient there, there is a horizontal asymptote at y equals 2 over 1, so y equals 2. Now, just like we had an example before, notice that x squared plus 1 can never be equal to 0 because x squared can't equal negative 1. So we are not going to have any vertical asymptotes or holes. On C and D, if I factor my denominator, I can say, oops, 2 and 3. Those are bad inputs for x. Those are points of discontinuity. However, look how 2 makes both the top and the bottom equal 0. Also, so we'll notice that, and I'll move my paper in a second. Also notice that the exponent in the top, or the degree of the numerator, is smaller than the degree of the denominator. Therefore, the denominator is going to get bigger faster, so I'm going to have a horizontal asymptote at y equals 0. And I'm going to have a vertical asymptote only at x equals 3. There will be a hole at x equals 2. Now let's actually find the point again. This would reduce down to 1 over x minus 3. And if I input 2 right there, my hole is going to take place at 1. And again, if I plug 2 right there, I get 1 over 2 minus 3, 1 over negative 1. So I could just write it as the point 2, negative 1. That's where the hole is. Not to think that this x equals 2 is some type of an asymptote. It's just the location of where the x-coordinate, where there be a hole. It's actually that point is the hole. Now last one. Numerator power is bigger than the denominator. So what type of a horizontal asymptote will we have? None. There won't be one. Our graph is just going to get huge as x gets bigger. I can see that negative 2 makes my denominator turn to 0. Oops, also makes my numerator turn to 0. So what will we have our vertical asymptote? None, because the numerator and denominator both turn to 0 with that input of negative 2. Now, this does reduce down to 3x. Once again, this function does not graph exactly the same thing as this function. They're very similar, though. This graphs just the line. This graphs the line with a hole at x equals negative 2. Now, the actual point of the hole will be at negative 2. Plug negative 2 back into here at negative 6. So it's going to look like the line y equals 3x, and then down here at negative 2, negative 6, there's actually going to be a hole. Okay, now you're ready to practice.